In the previous video, we talked about taking derivatives of vector functions. The natural follow-up to that is integrating vector functions. Recall that integrals and derivatives are basically inverse operations of each other. One way to say this is that if capital F prime of x equals little f of x, then capital F of x is the integral of f of x dx plus c for some constant c. While integration can be interpreted as the area under a curve, it will be better for the moment to think of it as the antiderivative. It's just a function that has this special derivative property. The concept of area doesn't quite extend to vector functions in a simple analogous way. But with that caveat in place, here's the definition. Definition: an antiderivative of a vector-valued function little r is a vector-valued function capital R such that capital R prime of t is equal to little r of t. The indefinite integral of little r of t is the general antiderivative of little r and represents the collection of all antiderivatives of little r. The last part of this statement is a reference to the constant of integration, which will also appear when integrating vector functions. There is not a single antiderivative, but an entire family of them. Just with derivatives, integrals are performed component-wise. The logic is the same, as the standard unit vectors can be factored out of the integrals. The key difference to notice, compared to single variable calculus, is that the integration constant is a vector, which means it will have 3 components. In other words, since there are 3 separate integrals, you will get 3 separate constants of integration, corresponding with each dimension. The most important application of derivatives and antiderivatives is in the relationship between position, velocity, and acceleration. Earlier, we talked about how you can start from the position vector of an object, take its derivative to calculate the velocity, and then take the derivative again to calculate the acceleration. Antiderivatives allow us to undo this pattern. If we're given acceleration, we can integrate it to get velocity up to a constant, and then integrate it again to get position up to another constant. These constants are often called initial conditions. With any one of these vectors and the right number of conditions, we are able to calculate all the others. We are going to apply these ideas to the problem of projectile motion. This is the theoretical motion of an object that is launched under the influence of gravity. What does this mean? Here's how we're going to set up the problem. We are going to work in 2 dimensions, with x being horizontal and y being vertical. The object is launched from the position x0, y0. The initial speed is v0, and the object is launched with an angle theta with the horizontal. The acceleration is the vector 0, negative g. Notice that this is saying that gravity is pulling in the negative y direction. We are going to ignore all the forces except for gravity, so there's no friction and there's no wind. This is a lot of little pieces of information, so we'll start by making a quick diagram of this to guide us as we work through the problem. We are in 2 dimensions. The object is launched from the position x0, y0. The object is launched at a speed v0 at an angle theta with the horizontal. The acceleration is 0, negative g. Since we know the acceleration, we can integrate that to get velocity. Notice that we need to solve for the constants of integration, which we have called v0x and v0y. To do this, we draw a right triangle with the initial velocity so that we can get the x and y components of it. We can plug this in to get the full equation for velocity. Then we can integrate this to get position. Notice that theta is a constant, so the sine and cosine terms are just constants with respect to t. It turns out that once you integrate and solve for the constants, you'll get this result. And this result is the equation for projectile motion. This is the type of calculation that you ought to be able to do on your own. By that, I mean you should be able to work with just these assumptions and arrive at the appropriate equation for the motion of a projectile. In some ways, I hope that if you have a projectile motion problem, that you will be able to derive your solution from first principles rather than just plugging values into this formula. I think you stand to gain so much more from the experience of working it out a few times than you do if you just jump straight to the formula. And that brings us to the end of this section. As always, please take the time to do the exercises and make sure that you understand what's happening in this section. Specifically, by this point, you should be very comfortable with vectors, vector notation, and vector operations. From here forward, when we need to use vectors, we're just going to use them without doing a big review of them.